Great. Okay, can people on Zoom hear me? All right, I'm going to assume it's all right. Today we will continue our discussion of, before I move on, I should say that I'm going to probably put I'll try to do like a little video tutorials on Qiskit for some of these problems. So I just think we are running out of time that I can't also go through the Qiskit parts in the class. And so what I'll do is I will set up a couple of these in Qiskit. I'll share the notebooks with you via GitHub, and then I'll do a little video tutorial with them. But the actual, the theory and the physics the physics and the theory of it, I will explain in the class. So you get a chance to go through the algorithm with me. But in terms of like implementing it on Qiskit, because that's a little bit, takes more time sometimes. So I'm going to try and do that offline, so to speak. But you'll have either the notebooks or the video tutorials along with it. So hopefully it'll be okay. All right. So today I'm going to start by quickly reviewing the Dutt algorithm. As you may remember, the problem was to determine if a function that returns a single bit is from an n-bit string is constant or balanced. And here was the implementation of the algorithm. We have the input qubits, n of them, and then we have one answer or ancilla or output qubit. There are all these names for this extra qubit that we use. And that extra qubit, it starts not in the state 0, but in the state 1, which is easy enough. We apply a NOT gate to the state 0, and then we apply a Hadamard. So this input, the answer qubit is in the state minus. And then the input qubits, of course, because of the Hadamards, are in a uniform superposition, which we discussed last time. And then when we apply the quantum oracle, that creates what we call the phase oracle, by phase kickback onto the input qubits, so the input qubits get a phase. So let's just quickly, and that first step, which is creating the uniform superposition of the Hadamards, the input qubits, I label that as rotate, right? That's the rotate step in the quantum algorithm, which is common to nearly all quantum algorithms. And so that's this step over here. We take the tensor state 0, which is basically all the n bits, input bits are in the state 0, and then apply the Hadamard to each of them. That gives us this uniform superposition. That is, every state 0, 0, 0 up to 1, 1, 1 is represented here with a weight that is the same. The answer qubit, as I said, is in the state minus, the output or ancilla qubit, whatever you want to call it. And because the ancilla qubit is in that minus state, the quantum oracle acts like a phase oracle on the input qubits and leaves the answer qubit unchanged. This is the phase kickback idea or identity that I showed you before. This is the compute step of the Dutt algorithm. So what happens is, now I'm just talking about the input qubits. We are ignoring the ancilla qubit because it's unchanged. So the input qubits, which started in the uniform superposition, when the oracle acts on them, because the ancilla qubit is in the minus state, that produces a minus 1 to the power f of x. Meaning, in that superposition, whenever f of x is, is 0, then it's going to give me a 1 that will keep that plus sign in the uniform superposition the same. And whenever f of x is 1, it'll produce a minus 1 on that state. So that's what will happen to the state. So the state is now massively entangled because it's got pluses and minuses, so you can't separate it out into a bunch of superpositions. Okay. And then at the third step in the Dutt algorithm, we use the Hadamards to undo the effect of the superposition state. in a pattern that tells us the answer. This is always the trick. We have to extract the answer from the pattern that is formed after the Hadamard's act on it. And so, as we showed in the last class, when we take this superposition with the -1 to the f of x created by the phase oracle, we apply the Hadamards to them. So now the Hadamard is acting on this state. So we have to know the action of Hadamard on each of these states in the superposition. Okay. And that we showed that the action of Hadamard on any given state, any n bit string basically, is given by another superposition, okay, which is also over all the uniform bit strings. So again, it's a uniform superposition, except that instead of all pluses, you get a minus sign whenever x dot y equals 1, meaning this is the AND of the n bit strings x and y. Okay, so x dot y represents xn minus 1 times yn minus 1 plus xn minus 2 yn minus 2 plus until x1 y1 plus x1 x0 y0. We discussed this in the last class, what this means. Okay, so that gives us this superposition over here. I should note one small change from the last class. I had used the number, the variable s for the thing in the superposition. So that's just a small change from what I had done in the class. From the lecture notes, you should just note that instead of using s in the lecture notes, I'm now using y in this summation. But it's just a dummy variable, so it doesn't really matter for what we use. So the final state, after I apply, the phase oracle and the final Hadamard steps of rotate, compute, rotate, at this point, the state has become this superposition. So we see a summation over all the y's, right? Y's are over here. So that's the quantum state. That's the the summation over all the input qubit states. And then wherever there is one of these states satisfies a -1 to the power of x plus x dot y, this is what is left behind. That's where you lay the minus sign. When f of x plus x dot y equals 1, for example. Okay. Okay, so what does this do? Well, when we measure the state, we're going to project it, right? Let's say we project it onto one. Of course, in the final measurement, we just measure, right? That's all we do. But we can get any of the patterns, right? We can get like, say, 0, 0, 0, we can get 0, 0, 1, etc., up to 1, 1, 1. We can get any pattern at any given time. But we can calculate what the probability is, say, to project onto onto the 0 state. And that is just simply given by this, because when we measure the state y equal to 0, that means that x dot y is 0, right? Because that's 0. Therefore, this is the output state with this probability. Okay, so the probability to get the state 0 on the output is this. Okay, well, as you can see from this pattern, if f of x is the constant function, right, then f of x equals f of 0, which is 0, and therefore this or whatever it is, let's call it it might be 0 or 1, of course, it could be either. But whatever it is, this pattern now is a constant for every term in the superposition. And that term is just -1 squared times f of 0. So -1 to the power 2 f of 0. Well, that's just 1 to the power 2 f of 0, which is 1. And that's summed over all the n bit strings. So that's 2 to the n. So 2 to the n and 2 to the n cancel out, you get 1. Okay. So the probability if the function is a constant function, whatever the value, whether f of 0 is 1 or 0, you get probability 1 to be in the state 0 at the end. So if it's a constant function, and if it's a balanced function, you can immediately see you'll get an even number of +1s and -1s, not necessarily even number, but it is even because there are n bit strings. But you can just say equal number of zeros and ones. -1s and +1s, because f of x is balanced, and therefore the superposition cancels out. So the probability to observe the state 0, 0, 0 is exactly 0 in the output. And this is our algorithm, the Dutt algorithm. Any questions about the steps? I mean, some of the math, if you're not sure, you can go back and look at it, but I just want to make sure everybody's clear on steps in the algorithm and how they are working. So one other question we should answer is, what is the complexity class for the Dutt-Jozsa algorithm? So for deterministic classical algorithm, for Dutt-Jozsa, we've already discussed this in the class, that your best approach is simply to query the oracle each time. And if you're lucky, you will get on the order, you may have to query half of them at least. Okay, so the worst case is you may get lucky, you may get it one time, but most likely case is you have to query at least half the queries, which is 2 to the power n minus 1. Okay, which is roughly order 2 to the power n. Okay, and then you may have to make one more query to determine if it's constant or balanced, but that plus 1 doesn't matter. So complexity class is basically super polynomial in n for deterministic algorithms. But it turns out that, and of course, the quantum algorithm, as we've seen, is just one query to the function. So it looks like this is a tremendous speed up over the classical algorithm. But it turns out that using a probabilistic algorithm, we can solve the Dutt-Jozsa problem also on the order of one query. Well, the reason for this is, if I, instead of like querying the oracle, one time, each time with a different input, I have to just query it with like random inputs. Okay. And essentially, once we query enough strings, we can bound the error probability. But this number of strings doesn't have to be proportional to n. For example, you can show that if you query it, say, 8 times, you can already reduce the probability of an error by like, down to 10% or 5%, whatever you want to do. Okay. So the error grows as the number of queries, but that is not a function of n, the number of bit strings, basically. So that's why it's also complexity 1, because it's just a constant number of queries, no matter how big the input size is. Okay. So the DJ problem then belongs to what is called the BPP complexity class, meaning it can be solved efficiently, very efficiently, order 1, on a probabilistic classical computer. This is like running a Monte Carlo simulation, for example. You run with n number of random inputs, and that n doesn't grow with the size of the number of bit strings, basically. And so that's what this BPP complexity class is. All right, I'm not proving any of these results. Okay, I'm just stating them without proof. That may be something you can explore on your own as well. Okay. All right, so now I want to discuss another problem, which is also similar to the Dutt-Jozsa, but it's slightly different. It's called the Bernstein-Vazirani problem. And the idea or the statement of the problem is, we have a secret n-bit key, S, okay? And this is the secret key. And there's a function f of x, which again takes us from n bits down to 1 bit, okay? And the function, essentially f of x, takes the dot product of the input string with the secret key. That is, f of x equals s dot x, where s dot x is again that dot product that we saw in the previous Dutt-Jozsa problem. Okay, so this is the function f of x. It's different from being constant or balanced, as you can see. So it depends on some secret key, S. Okay. And of course, the problem is find the secret key, S. Okay. The algorithm is identical to the Dutt-Jozsa algorithm. So no changes there. So the only thing that changes then, ignoring all the other, the ancilla qubit, remember, this is the state in the Dutt-Jozsa problem. Okay. This was the state that we had. Okay. And this state over here, f of x plus x dot y, now we just replace f of x with s dot x. Okay. So since f of x equals s dot x, this gives us minus 1 to the power s plus y dot x, where the s plus y is taken modulo 2, as usual. Okay. So s plus y denotes the bitwise addition with no carry, i.e. bitwise XOR, which is si plus yi modulo 2. Okay. So that's the usual addition that we carry out with binary digits, bitwise XOR. Okay, so that's pretty straightforward, I hope. Any questions on this so far? How this came about? How we got to this step?
You repeat the last statement.
This part?
Here, s plus y.
Yeah, this is just me substituting s plus minus 1 to the power s dot x over here, and minus 1 So that's s dot x plus x dot y. So that means s plus y dot x. But what I meant to say is s plus y, you have to think of what it actually means. It means it's not just addition, but it's addition modulo 2. That's all I'm saying. So now we want to know, remember our goal is to find the secret key, S, right? So how do we get that? Well, let's ask what is the probability to get the secret key on the input qubits. Okay, that is what is the probability that y equals S, the secret key. Okay. So what is the amplitude for getting that state S? So we project onto the state S. So when y equals S, bitwise XOR gives all zeros up there. So going back here, when S equal to Y, okay, then S plus Y is, yi plus yi. And so whether it's if it's 0, it's 0 plus 0. If it's 1, it's 1 plus 1, but 1 plus 1 is 0 again, due to modulo 2 addition. Therefore, Y with itself, or S with itself, S plus S, is always a 0. Okay? Is that clear to everyone? So when that's 0, then we essentially have minus 1 to the power 0. So again, this looks like the Dutt-Joseph problem. The answer is 1. Okay. Therefore, the measurement output immediately gives us the secret key. So in the Bernstein-Vazirani problem, whatever you measure on the output is the secret key. Okay. That's guaranteed, because the bitwise XOR gives us all zeros unless y equal to S. Okay? And therefore, what I mean is that the probability to be y equal to S is 1, which means probability to y not equal to S is obviously 0. So the output that you measure will always be the secret key. Okay? So that was easy enough, right? Hopefully, for everyone to understand that it's just like the Dutt-Joseph, except the function is looks a little bit trickier, but gives us the answer right away in the end. Okay? Any questions about the algorithm before I discuss the complexity class? Okay. So, classical solution needs at least n queries because you have n bits to the key, the secret key. Therefore, each time you need to query the oracle and get like one of the bits out. Basically, you get n equations basically, and those n equations will give you, the answer once you solve for them. Okay. And we can show that the probabilistic algorithm also needs at least one n queries. Okay. So there's no speed up between the probabilistic and the deterministic algorithm. But the quantum solution, as we saw, only needed one query. But still, this is a polynomial speed up. It's not that great, right? Because it's like, it's still efficient on a classical computer. You just do n times. You do an n query with the number of bits is not a big deal for a classical computer. So it's efficient in both classical and quantum computers. So I wouldn't really say that there's a speed up in either of these cases. So both the algorithms we've seen so far, as you can tell, either Dutt-Joseph or Bernstein-Vazirani, there's no real speed up in terms of like, why would you go to all the trouble of a quantum computer if, for example, the algorithm is reasonably efficient on both a probabilistic machine or even a deterministic machine in this case. Okay, so now we come to our first problem, which is called Simon's problem, where actually there will be an exponential speed up in the quantum computer. Okay? So this is the new problem. So in this problem, again, the function f of x now is slightly different. It doesn't produce a 1-bit output, but it produces also an n-bit output. Okay? And what we are told, we are guaranteed that this function f of x is equal to f of y only if x equal to y plus s. And y equals x plus s. Both are true. Okay? And that's double implication, meaning, if this is true, then that must be true. And if that's true, then this is immediately implied. Okay? By the way, I hope you can see that, even if I just gave you that statement, you can infer this statement. Because all you have to do is add s on both sides. Okay, then this is x plus s equals y plus s, but s plus s is 0, as we have seen before. because S XOR with itself is always 0. Okay. So the two, really, I didn't even need to tell you this part. Okay. Okay. That's guaranteed once you know X equals Y plus S. All right, so this is a period finding problem, as you can see, because, yeah.
What is X in this description of F?
It's another secret key. It's another secret key, exactly. That is, the function is periodic with an unknown period S. That's our problem here. Okay. And this period is also called the secret XOR mask. And you can see why, because it basically takes any input and masks it with the secret key S. Yes.
So I'm still a little confused. Where are we getting this function y from? Given that it takes in a function x.
It takes in a bit string X, and it guarantees, I'll show you an example in a second, but it guarantees that f of x is equal to f of y only if x equals y plus x s. Because x is a variable, right? So I can choose any two x and y's in that list. And I'm guaranteed that f of x equals f of y only if this is true. X equals y XOR with s. Yes. Here, I'll give you the example right here. Okay. So first, let's start with n equal to 3. So x can be any one of these inputs, right? And let's assume the secret key is some number 110. Okay. So basically 6. Okay, number 6. Well, now if I XOR x with s, bitwise XOR, you carry out bitwise XOR. Well, then this is 0, 0, 0 plus 110 gives me 110. When I bit XOR with this, I get 111. When I bit XOR with this, I get 100. Okay, and so on and so forth. Okay, so this is now just XOR with S, and you'll notice that there are pairing of the input strings. So the number of inputs is exactly sort of divided into half. Basically, there are pairs here. So for example, 0, 0, 0 is one paired up with 110. You can see 110 is paired with 0, 0, 0. Okay, so you can think of 0, 0, 0 and 110 as a pair. Same with 0, 0, 0, 0, 0, 1, 111, etc., etc. Okay, so these are like pairs of inputs. And as I said, it's automatically true if x equals y plus s, then y has to be equal to x plus s. It's already guaranteed. And I just give an example here. So for example, f of x doesn't have to be trivial, right? So I may map the input bits into some musical piece with some notes, and this musical piece sort of repeats with some pattern, okay? And the pattern is not known to you. Okay? You just get some notes coming out of the instrument, the function. I just took key of C here for my key, and then it just starts putting out some notes for you. Okay. And the idea is now that you should note that 0, 0, 0 is patterned up with 110, for example. So 0, 0, 0 and 110 produce the same output A, for example, and so on and so forth. Okay. So periodicity, of course, implies a lot of value repetition, but given large enough bit strings and some secret key, this thing may not even look periodic at all when you first look at it, because it may be difficult to discern the period. Okay, so for example, you can also think of this as basically a truth table, right? Once again, right? You have some numbers and then you have some outputs. This is a truth table. How many possible truth tables can there be? Let's talk about that for a minute. So I did 3-bit string. What about 4-bit strings? Okay, how many possible truth tables would there be? We have how many pairs for 4-bit strings, first of all? Yes? 8, right. So we have 8 possible pairs, right? And for each pair, we now assign again an n-bit string. So there are 16 n-bit strings, right? So that means for the first pair, we have all 16 possibilities, right? 16 possibilities for the first. But for the next one, we must have a different number, right? It assigns only to pairs. It's guaranteed that only that pair produces that output. Remember, that was the guarantee. So the next pair only has 15 choices, and so on. So we get 16 times 15 times up to 8, basically. So that's the answer. Yeah, I don't know what that number is, but you can now calculate that. Or 16 factorial divided by 8 factorial, if you like. It's just basically that. Same type of counting things that you have seen, I'm sure, many times, probability courses. Okay, so that's the number of truth tables. So you can see there's a lot of possible truth tables. And in fact, this solution, the classical solution for this, or classical algorithm for this, is equivalent to what's called finding a collision. That is finding two numbers x and y such that f of x equals f of y. This is called a collision. This is similar to those of you who know a little computer science. There's something called hash functions in computer science that take like inputs and map them to some lesser number of outputs. And so this is similar to breaking a hash function. How do you break a hash function? Is by finding collisions. And typically, these are shown to scale exponentially with the number of steps. So number of bits. So it's order 2 to the power n over 2. Okay. So this is an exponentially scaling problem as far as we know, the breaking of hash functions. Okay. At least good hash functions, I should say. There are always some that are not so good, and you can break them fairly easily. Okay. There's also some interesting equivalence with something called the birthday problem, which I'm sure you've all seen in probability class, where you're asked to say, okay, I have a bunch of people in a room. What's the probability that at least 2 of them share a birthday? Okay, and this is a famous probability problem, and you can find that it's it actually is much worse than you would think. Like to find like 50% chance, you only need like 20 people or something like that in the room, or even less. I forget the number now, but it's an interesting problem. If you don't know it, you can go and look this up. Anyway, okay, so now we'll come to Simon's. Is the problem or the statement of this, what this problem, this function does, clear to everyone? And what we're looking for? Yeah. We're trying to find that secret key, S, the period.
Okay.
Yeah. Once again.
And we're looking for, so you compared it to the birthday problems.
Yeah. How is it the same? Well, there are equivalences between the collision problem and the birthday. That's all I was trying to say. Okay. So classically, this is something that has been known for a while. Okay. All right, so what are the differences from the earlier algorithms that we have used? Here we are going to use all the qubits, not just the input and the ancilla, but I'm sorry, in our earlier qubits, we only cared about the input qubits at the end. We measured the input qubits, and the pattern that they had told us something about whatever we were trying to find. Here we're going to measure all of them, okay? We're going to measure both the input as well as the ancilla qubits. The other big difference is that the quantum oracle, and this is again, I am not putting for the answer qubits or ancilla qubits, which are here, I am not putting the X and the H gate. So meaning these states are going to remain as 0, 0, 0. They're not going to be switched over to the minus state that we had for the earlier algorithms, which means that what this oracle is, it's doing the regular quantum oracle business, it's not doing the phase oracle business here. Okay. All right. So those are the two big differences. And so now we can go into the algorithm. Oh, once again, we have already done many of these steps. So for example, all the input qubits, we've done a Hadamard. So this is the input qubits are clearly going to be in a uniform superposition when they start out. Okay. So we start with the input and ancilla qubits. We rotate the input qubits again to get the uniform superposition, while the ancilla qubits remain in the 0, 0, 0 state. Okay, so that's our usual step with the Hadamards. Okay, and then we use the compute step, and now we're using the oracle. So when we do the compute step, remember the oracle. What it does is in the ancilla qubits, it takes f of x and adds it to the input. So meaning it adds it to the ancilla qubit. So it takes all the zeros plus f of x. So everything remains the same, except that the ancilla qubits are now changed to the state f of x. Okay, that's what the regular quantum oracles are supposed to do, and that's what happens here. Okay, now at this point, actually, in some sense, if you might think, if I measure, if I measure this ancilla state at this point, let's assume it collapses. Okay, so let's assume that the ancilla state here collapses to some value, right? Whatever that is, we don't know, but it'll collapse to some value, right? When you measure some qubits, you get some answer at the end. So let's call that answer F naught. Okay, then we are guaranteed by the statement of the problem that whatever this F naught is, there are only two possible values of X that can give rise to this ancilla problem, ancilla number F naught, meaning the total state is there are two possible values of X. One is X naught, let's call it X naught. So F of X naught is equal to F naught. And the other one is X naught plus S, the secret key that we're trying to find. So the answer is right here. Okay, we have X naught, we have X naught plus S. If we can find out, which one it is, we are done. Okay, but unfortunately, we can't, right? Because when I measure this, first of all, as you may imagine, each time it's going to randomly collapse into one of these F naughts. We don't know which one. Okay, it could be any of the F naughts that are in our list. Say A, the first, like in that example, could be the node A, for example, or the node G, whatever. Whatever this node is, we have two possible values. Yeah, I wrote it correctly. Okay. We have two possible inputs, but we don't know which one we are going to get when we measure the input qubits. With probability 1/2, we will get either one. And so that's not enough information for us because each time when we measure, we may not get back the same F naught. So if every time we were guaranteed to get this F naught, then yeah, with two measurements, one time we'll get hopefully with probability 1/2 this one, and the other time with probability 1/2, we might get that one, and then we XOR the two and we get S. Okay. But again, this is going to scale badly with the number of qubits because there are 2 to the power n possible outputs over here. Okay, so you don't know which one you're going to get each single time. And then further, you only randomly will get one of the outputs each time. Okay. Yeah. All right, so we can't find it by just simply measuring over there, which is why if you go back over here, we have one more rotate step. So these are the input qubits, and they are rotated one more time before measurement. Okay, so that's what we will do. So let's look at this state here, and we now apply again our Hadamard to the input qubits. Okay. Oh, sorry, came out in the wrong order. All right. Yeah, no way to fix that now. All right, let's just put it up there. Sorry. So ignoring the bottom here, just look at the top. So that's our state, right, after the compute step, and we now apply the Hadamard, and we leave the output qubits, that is the answer qubits, alone. So that's just the identity on the answer qubits. Okay. So we are left then with F of X on the output, and on the input qubits, we again apply our Hadamard to the power n on X. Well, we've seen this many times. Hadamard to the power n on X is again produces a uniform superposition multiplied by -1 to the power x dot y. Okay, so y is the summation over all possible strings, but then multiplied by -1 to the power x dot y. Okay. All right, so hopefully this step to this step is no longer a problem. You've seen it in like 2 previous algorithms as well. Okay. And now we can ask what happens if we measure the output. Okay. Now we measure the output qubit. As we said, we may get F naught on that output qubit, and the answer qubits will be in the state F naught. Okay, that's what we just said. And as I said, there are only 2 possible values of X. We call them, say, F of X naught and F of X1, which give me this value F naught. Okay, so out of that entire huge superposition, right? Again, only there will be 2 values left in the superposition, both of which will give me F naught. And so that is this over here, X naught dot Y plus -1 X1 dot Y. Okay, those are the 2 possible answers that are values of X naught of X that can give me the same answer F naught on the ancilla qubits. And so out of, if you look one step ago here, there was a 1 over square root of 2 to the n over here, because that covers all the possible superpositions X that gives me this answer. But now out of all of those, only two of them will be left, and that is makes it go down to square root of 2. Okay. And then we have this minus 1 to the x naught plus y and minus 1 to the x1 plus x1. Well, again, we ignore the ancilla, it's in the state f naught, and we're guaranteed by the secret key s that x1 equals x naught plus s. So that whole state, that coefficient up there, so the coefficient of the state over here, right, is given to be minus 1 x naught dot y plus minus 1 x1 dot y. So that's the for any given y, of course, right? I mean, y is changing. There's still a summation over y left behind in that superposition. But for any given y, that coefficient is minus 1 x naught plus y plus minus 1 x naught plus s dot y, which I can simplify as minus 1 to the x naught dot y, and then just take it outside, and I'm left with minus 1 s dot y. Okay. Good. It's just, I'm just factoring out minus 1 to the power x naught dot y. Again, we know for any s, remember s dot y is just a single bit. It's the AND, bitwise AND of s and y. Okay, so the output is always going to be 0 or 1. If that value is 1, then this minus 1 will give me a minus 1, or it'll give me a plus 1 if the s dot y is 0. Okay. So the coefficient of y is given by one of these two possibilities. If s dot y is 0, it gives me 2 to the power 2 times minus 1 to the power x naught dot y, so that's what was common to both of them, or it will give me 0 for s dot y equal to 1. And so if I substitute all that back, out of all the possible y's, and going back here, out of all the possible y's that are possible, out of all the possible inputs, strings, y, only the ones such that s dot y equals 0 will be left behind. All the other ones will give me 0. All the other ones will not have any amplitude. That is, when s dot y is equal to 1, they just have a coefficient of 0. So in that whole pattern, only the ones that satisfy s dot y equal to 0 will be left behind. I don't care what's in this summation anymore, because I just know that I'm going to get some output y such that s dot y equals 0. So what I mean is, if I measure the input register, I'll only obtain values of y such that s dot y equals 0. That's guaranteed by this statement here, by the summation s dot y equals 0. Any value of y that I get, I may get any number of values. Each time I may get a different value of y. But every time I get that value, the summation guarantees that that value will satisfy s dot y equal to 0, which is, of course, an equation with n bits ANDed together equals to 0, modulo 2 as usual. Okay, the s dot y, this dot product, this is the meaning of it. So that is an equation with n unknowns. The n unknowns are the s n minus 1, s1, s naught. Those are the unknowns. So there are n unknowns. And this is one equation. Remember, y's will be given to us when we measure. When we measure, the input qubits will get some pattern of y's. Okay, we don't know what pattern. In any given run of the computer, we'll get some pattern y. Okay, but those will be known to us. So these yn minus 1 are known values, 1, 0, 1, 0, whatever they are, and we'll put them back into this equation. So this is a linear equation with n unknowns. Each time I repeat the algorithm, if I repeat it n times, the only question is, will I get a different y? Because if I get the same y again, it's a waste of my time. I've just got back the same equation. But if I repeat n times, I'm pretty certain to get, n different values. That's because, as I said, there are 2 to the power n bit strings. Because y is an n bit string, so there are 2 to the power n possibilities. So the probability that I get back the same y each time is very unlikely. Okay, so another way to say it is, if I have 2 to the power n strings y, there are only 2 to the power n minus 1 such numbers satisfying s dot y equal to 0. Okay. So I've cut in half sort of the space because there's either s dot y equals 0 or s dot y equals 1. Those are the only two cases. So therefore, out of all the 2 to the n, half of them will satisfy s dot y equals 0, the other half will not satisfy that equation. Therefore, we are left with 2 to the power n minus 1 numbers such that s dot y equals 0. Okay. So if I repeat it, each time I'm very likely with probability 1 over 2 to the power n minus 1, that will be it will not be the same number. So this is basically going to give me each time a different number. And once I have n of them, I just solve that efficiently, on your classical computer, n equations and n unknowns is very easy to solve. That will be efficiently solved for the secret key, Sn minus 1. So remember, the classical algorithm, which is the collision problems, requires searching through sort of this 2 to the power n minus 1 or 2 to the power n over 2 sort of solutions for the collision. Whereas here we can solve it with n queries to the oracle, plus some little bit of classical overhead for solving n equations in n numbers. Okay. Okay, so before I move on, any questions about this algorithm? Yes. You have a question? Oh, I thought you were raising it. I guess the trickiest one is just understanding, going from here. Hopefully this step was clear to this part here. And then after that, it's a bunch of reasoning about what the possible values are for the superposition. Okay. Yeah, I think that's the end basically, and that's the speed up of Simon's problem. Simon's algorithm. Yes.
So I got sort of lost once we rotated the input after computing.
After computing.
For like a couple slides back now. Yeah.
Yeah. Here. Here.
Yeah. So like
Yes.
I was okay with this, and then after this point, I sort of lost the picture. Could we maybe go through it again?
Yeah, absolutely. So up to here, you're okay?
Yeah.
Okay. All right. So at this point, remember when I first talked about measurements, if I hadn't done the rotation, suppose I had not done any rotation there. This is rotate, compute. And let's say I measure the ancilla qubit at that point. Right? F of x. Okay. I'll get some number, F naught, call it. Okay. At that point, as I said, you followed this step.
Yeah.
So you're guaranteed that you get x naught F naught plus x naught plus s F naught. Is this step clear to you?
I think so.
Yeah? Okay.
More or less.
If this is clear, then all that the extra rotation does is add a minus 1 to the power x naught dot y or a minus 1 to the power x1 dot y. That's what that extra rotation is doing. You can see that here. So same step, if I measure the answer qubit and I get F naught, then I get either x naught dot y or x1 dot y as the answer.
So in this x1, it would be x naught x or x from.
Yes, exactly. Right. X1 and x naught are related by the secret key S. Okay. They are the pairs in our inputs that are mapped to the same output. But as I said, we may get any of these pairs in any given answer. That's why we have to do this extra rotation to try and back out x naught from this superposition. And of course, because we did the rotation, we have again a sum over all possible states in the superposition. So it's a fairly complicated looking thing, but when you measure it, it collapses only to those values of y such that s dot y is 0. That's what that that thing did for us. By doing that extra step, we ensure that the output state always satisfies s dot y equal to 0. So it gives us some information about s in the pattern of values that we get out. Yeah. Okay. Okay, so now I'm going to move on to the next problem, which is called Grover's problem or Grover's search problem and algorithm that he invented. So this problem looks very similar to our Dutt-Joseph problem, for example, except the difference is that it takes n-bit strings and maps them to the value 1 if that input string matches something called the winner, okay, and is 0 otherwise. So what does this look like? Okay, so suppose I give you a phone book, okay, and many of you have not seen a phone book problem. I don't know. Okay, but reverse image search might be another example. But okay, let me just start with the phone book example because it's so standard in the literature. Okay, so a phone book is an alphabetized list of names with the number for each person in that phone book. Okay, so if you are given a name, it's fairly easy for you to find the person by their name because what you do is you divide the list into half, right? So you know that their last name is anywhere beginning from A through Z. Therefore, you divide, say, in the middle, and then you look. Okay, is the name, does the name start with a letter less than the middle or greater than the middle? And then if it's less than, then again you divide that list into half, and you keep doing this till you find their first letter, and then you look in that list for their actual name, right? So you can see that it's fairly efficient if you're given the names and the numbers to look up by name. So if you're given X, so to speak, it's easy to find what the value of the f of X is going to be. Okay. This problem, though, is the opposite. I give you the phone number and I ask you to find the name. So now you have no choice but to look through the entire list of phone numbers, hoping to find the right phone number that matches the number that you were given, and then look up their name. So this is the inverse function, as we call it. It's an invertible map, right? We need to find that inverse, basically. Okay. And this is an unstructured database because it's just ordered by phone numbers, and there's no order, right? The phone numbers are randomly assigned to each person by their name, but you're trying to find the name. So you don't have that name information, so you can't find them easily. So this is there are other examples. Reverse image search, for example, would be a similar idea, So this is an example of invertible function lookups, okay? And this could be used to, for example, solve NP problems. You may remember when we defined an NP problem, we said an NP problem is one where it's easy to verify the solution once you have it. And that's exactly the situation, right? If I give you the name, it's easy to verify that that name has that phone number, okay? But if I give you the phone number, then it's the opposite problem and you can't look at it. And in fact, one of the ways to solve NP problems, if, Grover's algorithm, as we'll see, it doesn't give us enough of a speed up to allow us to solve NP problem. But one way would be simply look through every possible solution, right, to the NP problem and see which one is correct. If you could search all those problems, basically. Yeah. So you just check each input to see which output is correct. But that would take forever, basically, in NP problems. So that is the issue of unstructured database search, or basically reverse image lookups, etc. All these are difficult problems to solve if you don't have any structure to them. So the oracle function, as I call it here, right? This is the oracle that we are given, is essentially marking for us the answer. It tells you 1 if you have the winner, the actual answer, x equal to w. So w is the winner, and then 0 otherwise. It marks that input correctly. It tells you what the answer is. Okay. But you don't know what that is because you can't look it up. Okay. All right. So now we start again with the n input qubits and 1 ancilla qubit, and we create the uniform superposition of all the input qubits. Okay. So again, in our standard way, we take all the input qubits, apply the Hadamard, and we get the uniform superposition. And this time we're going to use the phase oracle. So the same quantum oracle, but now we're going to start the answer qubit or ancilla qubit in the state minus. Okay. So as usual, by applying X and Hadamard gate as usual. So at this point, let's go through a little bit of the math. So first of all, we'll write 2 to the power n, which appears in the superposition as capital N. Okay, just to make it a little easier in the notation. Okay. And we know that only one of the states is the winner, right? Whichever that winner is, we don't know, but we know only one of them is the winner. Okay. Okay, so we have for the input qubit, the state W, which is the winner, and then all the other states which are not the winners. Okay. I don't want to use the L word here, but you know what I mean. Okay. Sorry. Okay. So that means I can rewrite the superposition as 1 over square root of n W plus something times I, which is still 1 over root n times the summation I not equal to Wi, and I'm now multiplying and dividing by the same factor, square root n minus 1. Okay. And I'm going to call this factor here 1 over square root n minus 1, summation I not equal to Wi as R. Okay. R. Okay. So all of this stuff here is just R multiplied by some factor. Okay. So rewriting that is just 1 over square root of n W plus square root n minus 1 over n R. Okay. And because these two, as you can see, squared, if you take the square of this and the square of this and you add them together, that gives you 1, right? Because it's just 1 plus n minus 1 divided by n. Okay. Which means cos squared theta plus sine squared theta equal to 1 means I can call this 1 over root n as sine theta. Okay. Remember, n is very large, right? So n is very large. So in this uniform superposition, the probability of being in the winner state is very small, right? It's 1 over square root of n. So the probability is 1 over n, which is very small. And the probability for this one is very large, right? To be not in the winner state. Okay. All right. So that's sine theta W plus cos theta R. Okay. So now this gives us a nice pictorial view. R is a uniform superposition over all non-winners. And theta, as you've seen, is defined in terms of n. So simply sine theta equals 1 over square root of n, cos theta equals square root n minus 1 over n. So basically, at this point, after the uniform superposition, we can write the state that is created by the Hadamards in terms of R and W by this equation here, right? So this equation here tells us that the input state is in a state which has some small component along W and some very large component along the other states, R. So graphically, I can write that or show that in this way. Okay. So this is a very huge Hilbert space. So, but I'm just simplifying it to look like it's in 2 dimensions. One is the winner state and one is all the other states, which are a uniform superposition over all the other states. And you can see it makes a very large angle with those non-uniform, with those non-winning states, and a very, it makes a very large angle with that. So it's not at all, on that W. Okay, it doesn't look like W. S is mostly along R, basically. Okay, so we need a way, so to speak, to amplify this angle and get it so that S is closest to W, basically. That's what we want to do. Does that make sense? This is the pictorial representation, right? So that'll help us to understand the steps that we're going to have to do. Okay? Our goal is somehow to keep amplifying S until it ends up, or the angle theta, until it ends up being almost equal to pi over 2. So that's what Grover's algorithm does. Okay? So we query the phase oracle first. Okay, remember we have the phase oracle as usual. Okay, and remember the phase oracle always, what it does is it produces, if I were to just go back to the step, it will produce -1 to the power f of W plus -1 power f of I on each of the states when I query the phase oracle. Because remember, the answer qubit, the ancilla qubit has been put in the state minus over here. So whenever I do that by phase kickback, I put -1 to the power f of x on these input qubits. So that's this step over here. And I'll show you the circuit in a minute, but yeah, or maybe not today, but we'll see. -1 to the power f of w, okay, sine theta w plus -1 to the power f of r cos theta r. Basically, this is the effect of the oracle. Once again, okay. Similar to all the previous cases. Well, we know f of w is 1 and f of any of the other non-winners is 0. That's what is guaranteed by the oracle function. So we now see that the output after we query the oracle is minus sine theta w plus cos theta r, which means we have reflected the state. Remember earlier, the projection of s onto w was sine theta. Now it's become minus sine theta. And it remains the same along r. So along r is still cos theta. So that's basically inverting the amplitude along the w state. Therefore, that makes it go negative, and therefore we get a reflection around basically the r line, around the r axis. Okay? So instead of making an angle theta this way, it's now making an angle theta this way. Okay. Well, at this point, we are going to use one other gate, which I don't tell you yet how we make this gate, but pretend that we know how to make a gate that reflects the state around this S. Okay. So we make a gate. So remember now the state was originally here, making an angle 2 theta with respect to S. When I reflect it, again, it's going to do the same thing. It's just like a reflection around this mirror plane S, which means it's now going to make an angle 2 theta with respect to S. Okay. So we see that we have changed the angle from theta. Initially, we started in the state S, and after these two reflections, we've ended up with an angle 2 theta with respect to r. Okay, so whatever we were initially theta, we have now become 2 theta with respect to r. So if we keep doing this each time, we rotate by 2 theta each time, okay, until the state we can see will eventually approach the value w, okay, the ket w. Here. Let's say we do this m times, okay, and we need to find out how many times we need to do it. That's what we're interested in, okay. So because each time, remember, is a query to the oracle followed by this reflection r. Okay, so we're using this query to the oracle as our idea of circuit complexity or complexity class. So let's do m queries to the oracle followed by the reflections till the state is close to w. And at that point, theta plus m of 2 theta is equal to pi over 2. Okay. And that gives me m equals pi over 4 theta minus half. Easy enough to solve. And now we ask ourselves, what is this m equal to in terms of n, the total number of bit strings in the problem? Okay. Well, theta, as you may remember, was simply sine inverse of 1 over root n. And for small theta, that means basically this is approximately 1 over root n, which is true because as soon as n becomes large number of bit string or large number of bits, which means n is 2 to the power n, this is going to definitely hold quite accurately. Okay? So substituting that back into the expression for m, we see that m basically goes as square root of n. So this gives us a square root of n speed up over normal search. The normal search is going to take me at least n queries or n over 2 queries. Okay? This gives me square root speed up in that. It's not as good as polynomial, but it's still much better than just basic searching with a classical algorithm. Okay, so I think that's all I have for today. I didn't realize we were going to go this fast, so maybe I've gone too fast. And we can certainly open it up for discussion some more. So next class I will show you 2 things. One is how to make this reflection gate RS, and then we can discuss how once we know RS, how to create it with like regular gates, regular Hadamards and C0s and CZs and so on. We haven't discussed that at all. So that's something that we still need to talk about, but we'll do that next class. I think this is enough for today in terms of the problems. Does anyone have questions about the algorithm, Grover's algorithm? As long as this intuitive picture is clear to you, hopefully the rest of it, it's a little bit of math, but it's hopefully won't be too challenging. But before you do that, you need to know why we're doing all that stuff. Helps to have this picture. Yeah, so square root of n is still not great, but it's better than, I guess, anything else we have, unless somebody comes up with a better algorithm to like do the unstructured search, database search. I think this is still controversial, this Grover's algorithm, in terms of like whether it constitutes a true, speed up over regular algorithms. So I've even seen some recent papers claiming that, there is maybe not as much speed up as Grover claimed, things like that. So it's still actually a little bit of, controversy. I mean, that's one paper. So, I haven't fully researched and made sure they have been careful in what they say. So, yeah, yes.
These algorithms like
Yeah, I mean, that's the problem, right? I mean, which is what I talked about at the beginning. In the NISC era, they've all been done, everything from like, Dijosa to like Grover to like even Shor's algorithm, which we'll talk about. I don't know how deep we'll get into it, but all of them have been carried out, but usually with like small number of qubits. So it never usually makes a speed up for over a classical computer, right? The only time you win is if you get to like very large numbers of bits. That's I think one of the slides I had at the very beginning of the class, which we are not yet in that regime in the hardware. The hardware is not good enough yet to see a speed up in these problems. Now, there is that one problem which is called the sampling. There are two types of sampling problems that I explained to you in the beginning of the class. I gave you some reading material on them as well, which is one was a circuit complexity, basically that Google demonstrated a couple of years ago, but that's the problem which really has, as far as we know, no application. Meaning, it's not a problem that somebody needs to solve to figure out something, for example. Okay. Now, some of the problems in your term projects are actually problems that people care about. Like for example, variational quantum solvers, they say, could be used to, for example, find the ground state of a molecule, energy of a molecule. It's a more physics problem, obviously, not a direct computational problem, but still an interesting problem. And then there are others like solving linear equations. So there are a few that people think we have algorithms that will be better, but again, we're not in the regime yet where they truly are going to speed up computations a lot. But I think that's where the focus is right now, is improving the hardware enough that by implementing one of those algorithms, we get at least acceleration over what a classical computer can do. And that's actually one of the big sort of goals for most people right now is, using the quantum computer, not directly as a universal computer, but to use it as an accelerator for like problems that are, there may be one step that a classical computer has a hard time doing. Like, for example, finding the ground state of some molecule, which the quantum computer can come in, and if it can solve that part, then the rest of it might go faster on a classical computer. So I think that's sort of a big area that people are very interested in attacking right now with NISC hardware. Yeah. Okay. So yeah, just to summarize, all of these have basically used a very similar format of the rotate, compute, rotate, and we'll see this again and again. The tricky part is always figuring out, what the oracle has to be and what the right way to do the rotations has to be to back out the answer. So for example, in the next one, we'll see there's a particular pattern of gates that we can apply for carrying out, say, quantum Fourier transform, for example. And this will be another example of something where the quantum computer can do it more efficiently than a classical computer. But, these are, as I said, it requires a lot of thought to like figure out when the quantum computer will give you an answer that can be faster. Because as you've seen, just simply querying the oracle in the Simon's problem, I won't go back over it, but simply querying the oracle and then trying to measure will not get you anywhere, because as you saw, it'll result in some uniform, random state, and just looking at the output or the input qubits in that random state doesn't give you usually enough information unless you're clever. And there has to be some structure in the oracle or in the problem that really gives you the speed up. So that oracle or that speed up comes from some structure in the problem. And there's a lot of research going on into what kind of structure has to be in the problem, whichever problem you're trying to solve, so that a quantum computer can give us a speed up. Okay, so that's still a research area, I would say. Okay, but yeah, these are the first sort of algorithms that you're seeing where there is a speed up over classical computers, or at least Simon's problem and Grover's problem are those speed ups. Okay, guess I'm done for today, and see you all next week. Have a happy Easter.